Hello, we are senior chemical engineering students at the University of Nevada, Reno. Our particle technology project was the creation of a spray dryer. Our group, Team 5, consists of Christine Feeney, Andrew Gentry, Riley Kessinger, and Angelo Lorenzo. A spray dryer is a device which transforms a liquid feed into solid particulate in one operation. This is done in 4 steps: atomization of the liquid feed, contact with hot air, rapid evaporation, and product recovery. Atomization of the feed is the most important step and is used to increase the total surface area of the liquid, which allows for rapid drying when the droplets come into contact with hot air. In industrial spray dryers, atomization is usually accomplished using rotary atomizers or hydraulic pressure nozzles. Hot air can be added to the system in countercurrent, co-current, or mixed flow. According to Perry's Chemical Engineer's Handbook, co-current is the best option for heat-sensitive particles. During evaporation, the solids in the droplets are kept cool as the moisture evaporates. The droplets may shrink, expand, fracture, or agglomerate during this stage. In most industrial systems, a cyclone may be used to collect the particles continuously. Spray dryers have important uses in the pharmaceutical industry. In the 1940s, they were used to create infusions, extracts, medicinal salts, adrenaline, and vitamin C. Today they are used mainly for microcapsules and inhalable drugs. A new drug which uses spray drying is estimated to be created at least every 2 years. Spray dryers also have important uses in the food industry. They can be used to make food products such as powdered milk, tomato powder, and dehydrated water. Spray dryers are used in the food industry because they are great for turning liquid into solid particulate with no extra work involved. They allow for hygienic drying conditions, do not ruin taste or nutritional value of food, and it is more economical than alternatives such as freeze drying.
According to Perry's, spray dryer chamber design is complex and sizing should normally be done by manufacturers. Due to the complexity of the design equations for spray drying, many assumptions were made to simplify the process. The team assumed that droplet size would remain constant as a droplet dried. An evaporation model was used for pure water, not milk. Only terminal velocity was accounted for in calculations, and the terminal velocity was calculated neglecting any resistance from countercurrent airflow. The calculations performed led to a dryer height of 1.52 meters and an operating temperature of 525 degrees Celsius. The duct used was exactly 1.524 meters in height, but using one hot air gun in countercurrent, the operating temperature of the system reached equilibrium at only 150 degrees Celsius. Due to the increased residence time created by countercurrent flow and the likely overestimation in the required chamber height, the team decided that experiments were still likely to be successful at 150 degrees Celsius. This is an image of the 5-foot-tall galvanized steel duct used as the chamber for spray drying. Other materials used included a 1-foot by 1-foot aluminum sheet used as the cap at the top of the duct. The duct was covered in faced fiberglass insulation as seen in this picture for safety purposes as well as to conserve the heat energy given off by the relatively small flow rate of the hot air gun. A paint airbrush, which released droplets of 300 micron diameter, was used as the atomizer. A thermometer was used to monitor the temperature of the system at all times. A hole saw was used to create an opening for the hot air gun. Duct tape was used to secure the insulation. A pizza pan was used to collect the powdered milk at the bottom, and milk was used as the liquid feed. This picture shows the opening made at the bottom of the duct for the hot air gun to be inserted into. The air gun was also holstered onto the duct so that no one would have to hold the air gun in place during operation. A pressure release opening was created at the top to avoid any hazard of a dust explosion. This opening also served as a safety measure so that all operators would know where the hot air would exit the chamber. A video showing operation of the spray dryer will be shown on the next slide. After several hours of experimentation, 4 grams of burnt milk powder were obtained. The powder was burnt due to the countercurrent setup, as well as the non-continuous removal process, which allowed milk to sit as solid matter on the bottom. At first, the 300 micron airbrush was used as the atomizer, but after 2 hours of testing, only 1 gram of milk powder had been collected. Milk began caking on the nozzle so that it would not spray properly. Also, since the airbrush created such a fine mist, it took a very long time to get through a relatively small volume of milk. Eventually, a weed sprayer was purchased in an effort to collect enough particles to sieve. The droplets created by the weed sprayer were far larger than those created by the airbrush, so the spray dryer worked, but not ideally. There was some liquid milk pooled in the center of the pizza pan, but significantly more solid particles were collected around the edges of the pizza pan in a shorter time period. Tyler sieving was used to determine the size distribution of the milk powder particles. An unusual and unexpected amount of our particles were of the largest measured size. Accounting for these particles, the average diameter was 237 microns. Neglecting these largest particles, the average diameter was 179 microns. According to literature, the average particle diameter for whole milk powder was 130 to 165 microns. The discrepancy in our data compared to theirs could be due to our small sample size and likely agglomeration of particles.